Hello everyone. This is Dr. M. Pavan Kumar Reddy, Assistant Professor, Department of Mathematics, VNR JYOTHI Institute of Engineering and Technology. Today we'll learn the reduction of quadratic form to canonical form by orthogonal transformation. So what is the procedure? First, we study what is the procedure to reduce a quadratic form to canonical form by orthogonal transformation. See, we see step by step. First, write the symmetric matrix A associated with the given quadratic form. See, as we know that X transpose AX is the given quadratic form. So if quadratic form is given, we know how to write a matrix. We studied it in the last lecture. Okay, X transpose AX, A is the matrix of quadratic form. Okay. Second step, find the eigenvalues. Since I am discussing the case for generalization, n variables. Okay. So it is an nth order matrix, so there exist n eigenvalues. So eigenvalues are say lambda 1, lambda 2, lambda 3, so on, lambda n. And we determine the corresponding eigenvectors x1, x2, x3, so on, xn. So n eigenvalues and n corresponding eigenvectors of the matrix. So first step, we write the matrix of quadratic form. Second step, we determine the eigenvalues and eigenvectors. How to determine eigenvalues? So we write the characteristic equation, okay, which is an equation of degree n. So we get n roots. So those are lambda 1, lambda 2, so on, lambda n. Okay, and corresponding to every eigenvalue, there exists an eigenvector x1, x2, x3, so on, xn. Okay, and now after determining the eigenvectors, we have to normalize these eigenvectors. And remember, these eigenvectors x1, x2, x3, so on, xn must be pairwise orthogonal. So x1, x2, and so on, xn, all these vectors are pairwise orthogonal. Pairwise orthogonal. What is mean by pairwise orthogonal? Pairwise orthogonal means, see, x1 transpose x2 is equals to 0. x1 transpose x3 is equals to 0. Similarly, this is possible for all x1 transpose xn is equals to 0 and x2 transpose xn, x3 transpose xn, and so on all. All are pairwise orthogonal. Okay, if all these are pairwise orthogonal, then we have to construct the normalized eigenvectors. Normalized eigenvectors. Construct normalized eigenvectors. Let us denote these normalized eigenvectors with E1, E2, E3, so on, En. These are corresponds to lambda 1, lambda 2, so on, lambda n. What is mean by normalization? Okay, so see here, which are pairwise orthogonal. These are pairwise orthogonal. Okay, so define after this. Okay, so before this, how to normalize the eigenvectors? See, this is normalizing the eigenvectors. So what is normalization? Dividing the vector with its magnitude. What is mean by magnitude? What is mean magnitude? Say, if you have a vector x, with elements, say ABC, I'll consider only 3 elements in the vector. Okay, I'll explain. That can be generalized to any number of variables. That means it is actually that norm of a vector, that is magnitude of a vector, is nothing but some root over square root of sum of squares of elements of the vector, say a square, b square, c square. If you consider ABC, are the elements of the vector x, then its magnitude is square root of sum of squares of the elements of the vector. That is called magnitude. So to normalize a vector, we have to divide the vector with its magnitude. Then you get the new vector, which is called normalized eigenvector. Which is denoted with E1. If you divide x1 with its magnitude, you get E1. x2 with its magnitude, E2, and so on, like that. So after determining these normalized eigenvectors, we have to construct a matrix P. Which is called model matrix. This is called model matrix. P. So one column. Of course, this order is immaterial. It is need not be E1, E2, E3, so on, En. You can take En minus 1 and so on, E1 also. E2, E3, E1 like that, so on also. That's your wish. The order is immaterial. Okay, so E1, E2, E3, so on, En are the normalized eigenvectors. So writing these as the columns of the matrix, we construct a matrix called model matrix. Model matrix. And remember, this model matrix P is an orthogonal matrix. This model matrix P is an orthogonal matrix. So in the step 4, we have to define a transformation. We have to define a transformation. So after constructing this matrix P is now known. Why? Define a new vector. Already X is the vector, variable vector from the given quadratic form. Define a new variable vector, say Y. Suppose if you consider it's a 3 variables quadratic form. So let us take y1, y2, y3 as the variables. And P is the matrix already we obtained is a model matrix which is orthogonal. X equals to Py. X equals to Py. That is X is, remember, I'll explain this one with, anyway it is generalized. X is a n by 1, n variables, one column, and P is n by n. Okay, and Y is n by 1, in general. So now, if you multiply these two matrices, the resulting matrix is of order n by 1. And corresponding elements are equal. If left-hand side matrix is n by 1, right-hand side matrix is n by 1, the corresponding terms in the two sides are equal. Then you get x1 equals to something in terms of y1, y2, y3, so on. x2 is equals to, x3 is equals to, and so on. If you substitute all these in the given quadratic form x transpose ax, which is reduces to y transpose dy, which is reduces to y transpose dy, which is the canonical form of the given quadratic form, which contains, remember, only square terms, which contains only square terms, because P transpose A into P is a diagonal matrix. P transpose A into P is a diagonal matrix. See here, so that the model matrix P here is an orthogonal matrix. What does it mean by orthogonal matrix? P transpose into P equals to, or P into P transpose equals to an identity matrix. This is called an orthogonal matrix. If this satisfies, it's called an orthogonal matrix. And if you multiply these P transpose A into P, A is given matrix of quadratic form, P is the model matrix. If you multiply these three matrices, you get only a diagonal matrix, and also the diagonal elements are lambda 1, lambda 2, lambda 3, so on, lambda n. What are actually lambda 1, lambda 2, lambda 3, so on, lambda n? Are eigenvalues of the matrix A. Are the eigenvalues of the matrix A. Nothing but the diagonal matrix so obtained contains diagonal elements are the eigenvalues of the matrix A only. Are the eigenvalues of the matrix A only. But here remember, the model matrix P, how you constructed, like that only you get the corresponding eigenvalues. That means if you consider there are only 3 variables and 3 variable quadratic form, there exist 3 normalized eigenvectors E2, E3, E1, E2, E3. Okay, these corresponds to lambda 1, lambda 2, lambda 3. Then the diagonal matrix also you get DIAG, lambda 1, lambda 2, lambda 3. In this order you get. Suppose if you construct the model matrix as E2, E3, E1, you get the diagonal matrix with the diagonal elements lambda 2, lambda 3, lambda 1. That is the difference. That's it. Okay. So order of, while forming a model matrix, the order of a normalized eigenvectors is immaterial. Okay. One can take in a different way. Now, this transformation we substitute in the given quadratic form, x transpose Ax. That is, see here, as we know, Py transpose A. I'm just substituted. Now, as we know, AB transpose equals to B transpose A transpose. And as we know that P transpose AP, if you multiply, you are going to get a diagonal matrix. So Y transpose dy. If it is a diagonal matrix, as we know that while constructing a matrix of quadratic form, diagonal elements are the coefficients of square terms. That means you get only square terms in the canonical form. You get only square terms in the canonical form. So this is the procedure to reduce a quadratic form to canonical form. I hope you understand. Let's discuss a problem, how to reduce a quadratic form to canonical form by orthogonal transformation. Let's see one example. See, this is reduce the following quadratic form to canonical form by orthogonal transformation, and hence find index, signature, and also nature of the quadratic form. Also, see here, along with that, also write the transformation that will transform it into canonical form. So this is the given quadratic form. Which transforms this quadratic form into canonical form? That also you have to write. Nothing but what is x, what is y, and what is z. You are substituting to reduce this quadratic form to canonical form. That also you have to determine. So we'll see step by step. Okay. So already you studied how to find eigenvalues and eigenvectors in the second chapter. Anyway, I'll explain one problem, this one, with again in detail how to find eigenvalues and eigenvectors. So first step, we have to construct the matrix of quadratic form. This is, so now step 1, the matrix of quadratic form. I am using the short form, say Q dot F dot, which is called quadratic form. Okay. The matrix of quadratic form, let us denote it with A, say. Denote it with A. Observe here, the number of variables involved are 3. Number of variables involved are 3. So you are going to get a third order real symmetric matrix. So now square terms first. Their coefficients are 6, 3, 3. So therefore in the order 6, 3, 3. Next coming to 1, 2 term. That means first variable into second variable. Its coefficient is minus 4. Carefully. Minus 4. Don't take simply 4. Coefficient is minus 4. Minus 4. Divide it with 2. That is minus 2. Share it to 1, 2 position as well as 2, 1 position. Next, similarly, 1, 3 position. That means first variable into third variable, xz. Its coefficient is 4. Divided with 2. It is 2 only. So, share it to 1, 3 position, 3, 1 position. And the coefficient of second and third variable, which is minus 2. Divide it with 2. We get minus 1. So, write it into 2, 3 position as well as 3, 2 position. This is the real symmetric matrix. Real symmetric matrix. So now this first step is done. Second step, finding eigenvalues and eigenvectors. So how to find eigenvalues, eigenvectors? We solve the characteristic equation. First we write the characteristic equation. Now characteristic equation of A is, it is determinant of A minus lambda I is equals to 0. Determinant of A minus lambda I equals 0. Determinant of A, what is mean by I? Identity matrix. What is, A is the matrix of quadratic form. I is the identity matrix of order A. So A is of order 3. So I is also of order 3. So I is order 3 means only it has diagonal elements 1, 1, 1. You are multiplying the identity matrix with lambda means you have lambda along the principal diagonal. All other elements are 0. Then what is A minus lambda I? It is only we have to subtract lambda from the principal diagonal elements. 6 minus lambda, minus 2, 2. And minus 2, 3 minus lambda, minus 1. Okay. 2, minus 1 and 3 minus lambda. Determinant is equals to 0. Of course, you know how to evaluate the determinant. Okay. Anyway, I'll explain in detail. Along the first row, I'm expanding the determinant. That is, so 6 minus lambda into, so delete the corresponding row and column. Okay. So 3 minus lambda into 3 minus lambda. So it is 3 minus lambda whole square. Minus 1 into minus 1, which is plus 1. Next, minus of this term. Minus, otherwise I'll write here minus 2. Into, delete the corresponding row and column. Minus 2 into 3 minus lambda. Minus 2 into 3 minus lambda. Minus 1 into 2. Minus 1 into 2 becomes plus 2. Next, plus 2 into, delete the corresponding row and column. Minus 2 into 3 minus 2 into minus 1. So it is minus 2 into minus 1. It is plus 2. And minus 2 into 3 minus lambda. So minus 2 into 3 minus lambda, which is equals to 0. Okay. Now, let's simplify this expression. See, 6 minus lambda into, it is lambda square, A minus B whole square, lambda square, minus 6 lambda, plus 9 minus 1, it is plus 8. Next, minus into minus plus 2. Minus 2 into 3, minus 6 plus 2, minus 4. And minus 2 into minus lambda plus 2 lambda. Okay. Next, plus 2 into, it is 2 minus 6, again minus 4. 2 into, okay, and minus 2 into minus plus 2 lambda is equals to 0. Let's simplify. It is first cube term, minus lambda into lambda square, it is minus lambda cube. Next, lambda square term, plus 6 lambda square, plus 6 lambda square, minus lambda into minus 6 lambda, plus 6 lambda, plus 6 lambda square, plus 6 lambda square, plus 12 lambda square. Next, lambda term, minus lambda into minus plus 8, minus 8 lambda, and minus 36 lambda. So, minus 44 lambda. And constant term, 8 6 are 48. Next here, it is minus 8 plus 4 lambda, minus 8 plus 4 lambda, which is equals to 0. Let's see, this is minus lambda cube plus 12 lambda square. Next, minus 44 plus 4, minus 40 plus 4, minus 36 lambda. And plus 48 minus 8 plus 40 minus, it is plus 32. So, plus 32 is equal to 0. Now, let's take minus common and write it is lambda cube minus 12 lambda square plus 36 lambda and minus 32, which is equals to 0. Okay. And of course, this is the cubic expression. You know how to solve this cubic expression. I am not going into the details. I'll write just the roots of this equation. The roots are lambda is equals to 8, 2 and 2. 8, 2 and 2. These are the eigenvalues of the matrix A. The roots of this equation are called the eigenvalues of the matrix A. Okay. So, these are the eigenvalues. Let's determine the corresponding eigenvectors. First, we'll see for lambda is equals to 8. See, what is actually, how to find eigenvectors? Now, we have to solve the homogeneous system A minus lambda into x equals to 0. So, now, for eigenvectors, we have to solve the system A minus lambda I into x is equals to O. Homogeneous system of equations. First, let's substitute for lambda is equals to 8. If you put lambda equals to 8, what we get? It is A minus 8i into x is equals to O. That means subtracting 8 from principal diagonal elements from the matrix A. So, what is a matrix A? So, this is principal diagonal elements. So, 6 minus 8. Okay, that is 6 minus 8 is minus 2. Okay. Next, minus 2, 2, minus 2, 2. So, it is minus 2, 3 minus 8. Minus 2, 3 minus 8 is minus 5, minus 1. Next, here it is 2, minus 1, 3 minus 8 is minus 5. So, this is the matrix. What is vector x? Let's take, you can take the variables x, y, z or x1, x2, x3, your wish. Let's take x, y, z are the variables, x, y and z. Okay, see here the variables are given x, y, z. Let's take x, y, z only. So, this is equals to 0, 0, 0. Observe here, this is the homogeneous system. How to solve homogeneous system? So, reducing it to echelon form first. Okay, applying the elementary row transformations. See, now using the principal diagonal element, what we have to reduce it to echelon form. What is echelon form? We have to make the elements below the principal diagonal to 0. We have to make the elements below the principal diagonal to 0. Okay, so that means minus 2, 2 and minus 1. Let's see. So, we have to use the corresponding principal diagonal element to make other elements in the column to 0. For that, what we use the row operations? It is R2 we have to change. R2 we have to change. How we change the R2? It is, so R2, see. So, operation. Both are same elements now. Minus 2, minus 2. Let's see simple subtraction. R2 minus R1. minus 2 minus minus 2, 0. So we are making this 0. Change happens to second row, remember. And next R3. Both are same elements with opposite sign. So R3, we change it as R3 plus R1. Don't use R2. Okay. R1. This element only used to make other elements to 0. So R3 plus R1. Let's make the changes. We are not changing the first row. Let's keep it as it is. Minus 2 minus 2 2. Okay. Second row we are changing as R2 minus R1. What is R2? Minus 2 minus of minus 2 plus 2. 0. Next, this is minus 5 minus of minus 2 plus 2. Minus 5 plus 2 minus 3. This is minus 1 minus 2. Minus 1 minus 2 minus 3. Coming to third row, R3 plus R1. 2 plus of minus 2. 0. Minus 1 plus of minus 2. Minus 3. Minus 5 plus 2. Minus 3. So now, first column, the elements below the principal diagonal element in the first column, 0. Next, this is X, Y, and Z. 0, 0, 0. Next. So now, next we have to make this element 0 using the corresponding principal diagonal element in the column, that is 2 2 position element. So both are same elements now. Let's do one thing. So changing R3 as R3 minus R2. R3 minus R2. Then what is the resulting matrix? You are going to get, it is first row we are not changing, so minus 2, it is 2. Second row we are not changing, 0, minus 3, minus 3. Third row we are changing as 0, minus 0, no. Minus 3, minus of minus plus 3, 0. Minus 3, minus of minus plus 3, 0. So it is X, Y, and Z. This is equals to 0, 0, 0. Rewrite the system of equations. It is now in echelon form. This homogeneous, this coefficient matrix is in echelon form. So now, rewrite the system of equations. That is minus 2x minus 2y plus 2z is equals to 0. And minus 3y minus 3z is equals to 0. Observe carefully here. We have only 2 equations, but there are 3 unknowns. 2 equations, 3 unknowns. In such case, we have to take one variable is an arbitrary constant. One variable is an arbitrary constant. So, number of equations are 2, number of variables are 3. So, therefore, nothing but rank of this matrix is number of non-zero rows are 2, r equals to 2. Number of variables are 3, r less than 2. Rank is 2, less than 3, number of variables. The system has infinitely many solutions. So, in such case, the excess number of variables are 3 minus 2. That is 3 minus 2. N minus r in general, it is 3 minus 2, which is one variable. One variable has to be taken as arbitrary constant. But which variable has to be taken as an arbitrary constant? Whether x, y, or z. So the variable which is common to both the equations has to be taken as an arbitrary constant. That means either you can take y as an arbitrary constant or you can take z as an arbitrary constant. So I will take z as an arbitrary constant. Let us take z is equals to say k, k1 or k. Okay. Z equals to I am taking k1. If z equals to k1, you substitute in the second equation, what we are going to get? Minus 3y minus 3k1 is equals to 0. If you simplify, what do you get? Y is equals to minus k1. Is that correct? See, minus 3y equal to plus 3k1. So 3 gets cancelled, y equal to minus k1. Substitute this y and z both in first equation. It is minus 2x. Next, y equal to minus k1. So it is plus 2k1. It is z equals to k1. So it is plus 2k1 equals to 0. That means that minus 2x is equals to minus 4k1. Therefore, what is x? X is equals to plus 2k1. Now, if you write the vector, it is x is equals to x, y, and z. So now it is, say, 2k1 minus k1 and k1. So this can be written as 2 minus 1, 1 into k1, where k1 is arbitrary constant. I'm not writing in full arbitrary constant. So k1 equal to 1, you get one vector, 2 another vector, 3 another vector, 4 another vector, -1 another vector. So like that you can have infinite number of solutions, but all are dependent, but we need only independent solutions. So we consider default, you can take k1 equals to 1, you get first eigenvector corresponding to lambda equals to 8. It is 2 minus 1 1. This is the eigenvector corresponding to lambda is equals to 8. Now in the similar manner, if you proceed, we get lambda for lambda equals to 2. Now for lambda is equals to 2, then the system becomes a minus 2i into x is equals to O. If you subtract this 2 from the principal diagonal elements, what we get? 6 minus 2, 4 minus 2, 2. Okay, and it is minus 2, 3 minus 2. Okay, it is 1 and minus 1. Next it is 2, it is minus 1 and 3 minus 2, which is 1. As usual, in the similar manner, you have to reduce it to echelon form. X, Y, Z, which is equal 0, 0, 0. Okay. Now, reducing it to echelon form, applying the row transformations, it is R2. Here we have minus 2, here we have 4. Multiplying the second row with 2 and adding it to the first, this becomes bit 0. That is 2 into R2 plus R1. Similarly, third row. Both are with same sign, 2 and 4. Let's multiply the third row with 2, 2R3 and subtracting the first row from this one. Now what is the resulting matrix? First row we are not changing, 4, minus 2 and 2. But second row as see here, 2 into minus 2, which is minus 4 plus 4, 0. And 2 into 1, 2, 2 minus 2, 0. And similarly if you proceed, you go through this, it becomes 0. Okay. Now rewrite the system of equations. It is 4x minus 2y plus 2z is equals to 0. So only one equation we have, but 3 unknowns. In such case, the excess number of unknowns can be taken as arbitrary constant. So that's why we'll take here, let say y is equals to k1 and z is equals to k2. Remember, this k1 is different from this. Okay, this is different. So y equals to k1, z equals to k2. Then if you substitute this y and z both in this equation, what we are going to get? See, it is 4x minus 2k1 plus 2k2 minus 2k1 plus 2k2, which is equals to 0. Which means simply I am writing, see, x is equals to, it is half into k1 minus k2. Let's see. If you bring these two terms to right hand side, becomes 2k1 minus 2k2. 2k1 minus 2k2. Okay. Now dividing it 4, we get 2 common and gets cancelled. So it is 2k1 minus k2. See, this is x equals to. Now what is the vector now? Now rewrite the vector x, y and z, which is half k1 minus k2 is the value of x1, y and z. So this is. Now let's write this vector as the coefficients of k1 and k2. As k1 coefficients are 1 by 2, 1, 0, 1 by 2, 1, 0. Say it is k1 plus k2 coefficient. What is k2 coefficient? Minus 1 by 2, 0, 1. This is k2. Where k2, k1, k2 are arbitrary constants. Where k1 and k2 are arbitrary constants. Now see here, lambda equals to 2, which is a repeated eigenvalue. So we have to get 2 eigenvectors now. So now say x2 equals to, here k1 equals to k2 equals to, you can take any values. Let's take to avoid fraction in the eigenvector, I'll take k1 equals to 2. Of course, you can take 1 also, no problem. But if you take 1, what happens? You get in the eigenvector fraction and a normalized eigenvector, and it will be difficult for computation purpose. So to avoid this fraction, I am taking k1 equals to 2. You can take 1, 2, 3, 4, 5, 6, minus 1, minus 2, like that, so on. I am taking 2 to avoid this fraction in the eigenvector. So if I take k1 equals to 2, we get it is 1, okay, it is 2, and it is 0. Now this is one eigenvector, say, and say x3 is equals to, it is again k2 equals to, I am taking 2. It is minus 1, 0, 1. Okay. Why I am taking this as these are two eigenvectors corresponds to lambda equals to 2. We have another property that if x1 and x2 are the two eigenvectors, if you have two eigenvectors, say x1 and x2, their linear combination is also another vector, another eigenvector. That means this is called linear combination. See, k1 into x1 plus k2 into x2. If you consider this is one vector x1, that is another vector x2, k1 x1 plus k2 x2 is an eigenvector we got. And you can separate this x1 and x2 as another two eigenvectors. So this is one eigenvector I am taking, this is another eigenvector I am taking. So now we got three eigenvectors, x1, x2 and x3 corresponds to three eigenvalues 8, 2, 2. Now we have to verify that whether these three eigenvectors are pairwise orthogonal or not. Okay, let's see. Now the eigenvectors are, now what are the eigenvectors? Let's write all the three at one place. So now the eigenvectors are x1 is equals to, it is 2, minus 1, 1. This is the eigenvector. Okay. Next x2 is equals to, it is 1, 2, 0. Okay. And x3 is equals to, it is minus 1, 0, 1. And here remember, we have one more property of eigenvalues and eigenvectors, that if eigenvalues are all distinct, the corresponding eigenvectors are pairwise orthogonal. The corresponding eigenvectors are pairwise orthogonal. That means that you no need to verify that whether the eigenvectors are orthogonal or not. You can directly construct the normalized eigenvectors. Construct the model matrix with normalized eigenvectors. But here observe carefully, these two eigenvectors are corresponds to same eigenvalue. So these two corresponds to distinct eigenvalue. This corresponds to 8, this corresponds to 2. And this corresponds to 8 and this corresponds to 2. These two are pairwise orthogonal, definitely. But these two corresponds to same eigenvalue. These may not be pairwise orthogonal. Let's verify that. Okay. So x1 transpose x2, which is equals to x1 transpose, okay, 2 transpose means row vector, and x2, which is 1, 2, 0. It is, this is 1 by 3 vector, this is 3 by 1 vector, resulting is a 1 by 1 vector, that is single element. 2 1 ja 2, next minus 1 into 2 minus 2, plus 1 into 0 0, so which is equals to 0. So x1 transpose x2 0. Similarly, if you consider x1 transpose x3, also this is 2 minus 1 1, and this is minus 1 0 1, and this is equals, if you multiply, minus 2, okay, plus 0. So this is minus 2 and 0 plus 1. Something we did wrong. Yeah. Sorry. See, here we have taken k2 equals to 2 now. So this is actually minus 1, 0, 2 it is. Minus 1, 0, 2 it is. So it is minus 1, 0, 2. This is the eigenvector. Now it is, this is 2. Therefore, 1, 2 is 2. The resulting is 0. Now x1 transpose x2 0, x1 transpose x3 0. Let's verify that whether x2 transpose x3 is 0 or not. It is 1, 2, 0, and it is minus 1, 0, 2. If you multiply, what we are going to get? It is minus 1 plus 0 plus 0. The answer is minus 1, which is not equal 0. So x2 and x3 are not pairwise orthogonal. x2 and x3 are not. x2, x3 are not orthogonal. So in such case, what we have to do? Since in order to, before normalizing, we have to get the pairwise orthogonal eigenvectors. So that let us do one thing. We'll take, this is, these two correspond. We take x1, 2 minus 1 minus 1 as one eigenvector. One among these two will be taken as one eigenvector. The another one will be neglected, and we determine a new eigenvector which is orthogonal to the remaining two. Let us take, I am removing x3 and I am replacing that x3 eigenvector with an unknown eigenvector, say ABC. ABC. Let x3 is equals to ABC, which is orthogonal to both x1 and x2. x1 and x2. So now we have unknown values ABC. Let's determine those unknown values. Okay. That means, so that is x1 transpose x3 is equals to 0. I'm not writing in detail. Like this matrix you can write x1 transpose x3. x1 transpose means 2 minus 1, 1 into this. That means I'll get 2a minus b plus c is equal 0 as one equation. And it is, if you do, it is x2 transpose x3 is equals to 0. You get another eigenvector, another equation. What is x2 transpose? 1 to 0. 1 to 0 means a minus 2b, a plus 2b is equals to 0. A plus 2b is equals to 0. These are the two equations we got. But there are three unknowns. Okay. Let's see from the second equation, we can write it as a is equals to minus 2b. Let's write this. From the second equation, you can write a is equals to minus 2b. Let's substitute this in the first. That is a equals to minus 2b, no? It becomes minus a equals to minus 2b. So substitute here minus 4b, minus b plus c is equal to 0. From this, what we have, minus 5b is equals to, minus 5b plus c is equals to 0. This means 5b is equals to c. 5b is equals to c. So from this expression, you can write a by minus 2 is equals to b. From this, you can write b is equals to c by 5. Let's equate these two. It is, we can write a by minus 2 equals to b equals to c by 5. This can be written as 1. Now you can take the values as a is equals to minus 2, b is equals to 1, c is equals to 5. Since all these three are equal, means all these three ratios are equals to some constant, say some k. So a equals to minus 2k, b equals to k, c equals to 5k. Let's take k is any arbitrary constant. K can be taken as 1. So that's why I'm taking a equals to b equal to c equals to minus 2, 1, 5 respectively. So that is the new eigenvector x3 is equals to, it is minus 2, 1 and 5. So now this is orthogonal to both x1 as well as x2. Now we have to normalize the eigenvectors. That is E1, E2, E3. So first we'll determine the norm of magnitude of these three vectors. So first, norm of x1. What is actually elements in the x1? A square plus b square plus c square. This is magnitude. 2 minus 1, 1. 2 square minus 1 whole square. 2 square is 4. 4 plus 1, 5 plus 1, 6. That means it is root over 6. Similarly, magnitude of x2, which is equals to root over. What are the elements in x2 we have? 1, 2, 0. Therefore, it is 1 square plus 2 square, of course, plus 0, which is equals to 2 square 4, 4 plus 1, 5. It is root over 5. Next, magnitude of x3. What is this? It is root over minus 2 whole square plus 1 square plus 5 square, which is equals to 2 square 4, 4 plus 1, 5. 5 plus 5 square 25. It is root over 30. Now we got all magnitudes. Now let's determine the normalized eigenvectors. That is normalized eigenvectors. Now E1 equals to, what is E1? It is x1 divided by magnitude of x1. What is magnitude of x1? 1 by root over 6. It is 2 minus 1, 1. So this can be written as 2 by root over 6 minus 1 by root over 6, 1 by root over 6. So this is the normalized eigenvector corresponding to x1. Now E2. E2 is equals to x2 divided by magnitude of x2. It is 1 by root over 5. It is 1, 2, 0, which is equals to, it is 1 by root over 5, 2 by root over 5 and 0 by root over 5, 0. Next E3. E3 equals to same x3 divided by magnitude of x3, which is equals to 1 by root over 30, which is minus 2, 1 and 5, which is equals to, it is minus 2 by root over 30, 1 by root over 30 and 5 by root over 30. Okay. So these are the three normalized eigenvectors. Next, what we have to do? We have to construct the model matrix. Construct the model matrix. P. Model matrix P. What is P? P is equals to E1, E2, E3. So we construct, we'll take E1, E2, E3, the normalized eigenvectors as the columns of the matrix P, which is model matrix. Of course, remember this is an orthogonal, which is orthogonal. Which is orthogonal. Okay. Now, what is P? I am writing here P. It is 2 by root over 6 minus 1 by root over 6 and 1 by root over 6. Next, it is 1 by root over 5, 2 by root over 5, 0. And it is minus 2 by root over 30, 1 by root over 30 and 5 by root over 30. This is the matrix P, which is called model matrix P. Now, we have to consider a transformation x is equals to py, which reduces the given quadratic form to canonical form. Okay. Now, the transformation is, let x is equals to p into y, which is the transformation. Okay. X is equals to p into y. Now, what is actually x? I'm not writing this, what is p here. Substitute. Now, the given quadratic form is, x transpose ax, no? What is x? Already we know this one. Py transpose a into py. Okay, this is equals to, it is y transpose p transpose a py. Of course, we know that, see here, as we know that. So now p transpose a into p equals to, we know that according to the procedure, p transpose a into p. If you multiply, see p you have here, write the transpose, a matrix of quadratic form, p matrix here. If you multiply these three matrices, you are going to get the diagonal matrix whose diagonal elements are eigenvalues in the order in which you have taken the eigenvectors 8, 0, 0, 0, 2, 0 and 0, 0, 2. 0, 0, 2. Okay. So now here it is y transpose and p transpose dy is dy. Now what is y transpose? Let us take y is the new variable vector, say y1, y2 and y3. Okay, D is the diagonal matrix 8, 0, 0, 0, 2, 0 and 0, 0, 2 into y is a vector y1, y2 and y3. Now, if you multiply, you are going to get 8y1 square plus 2y2 square plus 2y3 square. This is the canonical form, which is the canonical form. Canonical form of the given quadratic form, also called normal form, also called sum of squares form. These are the three names: canonical form, normal form or sum of squares form. Okay. Now, see, this is reduction of quadratic form to canonical. Now what we have done, let's recall once. First step, see the matrix, this is the quadratic form. First step, we have determined the matrix of quadratic form. Next, eigenvalues 8, 2, 2 and corresponding eigenvectors. Corresponding to 8 it is 2 minus 1 1. Corresponding to lambda equals to 2 it is 1 2 0 and minus 1 0 2. And we determine whether they are pairwise orthogonal or not. Since there exist repeated eigenvalue, we have to verify. If the eigenvalues are distinct, no need to verify. If eigenvalues are distinct, the corresponding eigenvectors are pairwise orthogonal. Okay, so here x2 and x3 are not pairwise orthogonal. So we instead of x3 we take the new eigenvector which is orthogonal to the x1 and x2 and ABC. Let us consider it is and determine it ABC values. And later normalize these three eigenvectors x1, x2, x3. You get the new eigenvectors say E1, E2, E3 which are normalized. Construct the model matrix P with normalized eigenvectors E1, E2, E3 and which is an orthogonal matrix. If you determine P transpose A into P, you are going to get a matrix D which is a diagonal matrix whose diagonal elements are the eigenvalues of the matrix A only and in the order in which you have taken the normalized eigenvectors to form the model matrix. Now we consider the transformation x equals to Py. Substitute, you get the canonical form, also called normal form and sum of squares form. Okay. Now what is index? See, first index. What is index here? Number of positive terms in the canonical form. How many number of positive terms are there? 8, 2, 2. All are positive terms. 3. So the number of variables in the quadratic form 3. Okay. And number of terms in the canonical form also 3. That means rank, it is a non-singular quadratic form. So that is R is equals to N. So first rank. Rank is 3. Index, number of positive terms 3. Signature. What is signature? Rank is R. Index S. Signature is 2S minus R. 2S means, say 2S 6 minus 3 which is 3. Number of positive terms or negative terms. Excess number of positive terms. Number of positive terms are 3 minus number of negative terms is 0. So 3 minus 0 is 3. Okay, this is rank, index, signature. Next, nature of quadratic form. What is nature? So remember rank equals number of variables. Okay. Next, and all the terms are positive. R is equals to N. So here according to this R equals to N and all are positive terms. S is equals to 3. Number of positive terms are 3. So therefore the nature of quadratic form is positive definite. The nature of quadratic form is positive definite. And finally what we have to determine? We have to also write the transformation which reduced the given quadratic form to canonical form. How to write the transformation? X equals to Py. Here we have taken the transformation now, but we did not determine that. So let's determine X equals to Py. So that transformation. So what is X? X is equals to Py. So X is equals to X, Y, Z. What is P? Is a normalized matrix with normalized eigenvectors. So 2 by root over 6 minus 1 by root over 6, 1 by root over 6, 1 by root over 5, 2 by root over 5 and 0 and minus 2 by root over 30, 1 by root over 30 and 5 by root over 30 and the variable vector, variables in canonical form y1, y2, y3. Now simplify. This is x, y and z. So the matrix 3 by 3 into 3 by 1, the resulting matrix is 3 by 1. See this, 2 by root over 6 into y1. So it is 2 by root over 6 into y1 minus first row with all. So plus 1 by root over 5 into y2 minus 2 by root over 30 into y3. Similarly, minus 1 by root over 6 into y1 plus 2 by root over 5 into y2 plus 1 by root over 30 into y3. And here it is 1 by root over 6 into y1 plus 0 plus 5 by root over 30 into y3. So this is. Now observe carefully. The left hand side is a matrix of order 3 by 1. Right hand side is a matrix of order also 3 by 1. So equating the corresponding elements, you are going to get the transformation which we used to reduce the given quadratic form to canonical form. So x equals to, it is 2 by root over 6 into y1 plus 1 by root over 5 into y2. This is minus 2 by root over 30 into y3. And y is equals to, it is minus 1 by root over 6 into y1 plus 2 by root over 5 into y2 plus 1 by root over 30 into y3. And finally, z is equals to 1 by root over 6 into y1 plus 5 by root over 30 into y3. So this is the transformation. The meaning of this is, what is the given quadratic form? XYZ. This is the given quadratic form. No. In this, if you put x is equals to this 2 by root over 6 y1 plus 1 by root over 5 y2 minus 2 by root over 30 y3, y equals to z. This xyz, if you substitute in the given quadratic form, you are going to get, and simplify, you are going to get this canonical form. Okay. So this is called the transformation which we used to reduce the given quadratic form to canonical form. Okay. So this is the reduction of quadratic form to canonical form. Okay. So this is the problem with the repeated eigenvalue. Let's see one more problem with the distinct eigenvalue. But here I will not explain in detail. Just I'll write eigenvalues, eigenvectors and normalized eigenvectors and the canonical form. Okay. This is the quadratic form given. Okay. So if you write the matrix of the quadratic form, I am writing just in rough. So 3, 5, 3. Okay. And the xy coefficient -1, and xz, it is 1, 1 here, and it is -1 here. So now the eigenvalues of this matrix are lambda is equals to, you get the eigenvalues are 2, 3 and 6. Okay. You get the eigenvalues of the matrix are 2, 3, 6. And the corresponding eigenvectors are x1 is equals to, it is -1, 0, 1. Okay. And say x2 is equals to, it is -1, -1, 1. And x3 is equals to, it is 1, -2, 1. So these are the eigenvectors. See here, no need to verify whether these are pairwise orthogonal or not. Since the eigenvalues are distinct, the corresponding eigenvectors are pairwise orthogonal. So directly you can normalize the eigenvectors, determine E1 is equals to, it is -1 by root 2, 0 and 1 by root 2. Okay. And E2 is equals to, it is -1 by root 3, -1 by root 3 and -1 by root 3. Okay. And E3 is equals to, it is 1 by root over 6, -2 by root over 6 and 1 by root over 6. These are the. Next, construct the model matrix P with the normalized eigenvectors as its columns. Okay. Then write the matrix transformation x is equals to py, and then x transpose ax is equals to, it is you get y transpose dy with it is 2y1 square plus 3y2 square and 6y3 square, which is the canonical form. All are positive. So index, I am not writing this formula, I will write s equals to 3, rank is equals to 3, signature is equals to 3, and nature is equals to, it is positive definite. Okay. And the transformation you can write x is equals to py. You substitute this x equal x1 xyz, you take y equal to y1 y2 y3 and write the matrix P and multiply, you get the transformation. So like this, we reduce a quadratic form to canonical form by orthogonal transformation. I hope you understand. Okay. So these are the worksheet problems. Let's work out these two problems, reduction of quadratic form to canonical form using orthogonal transformation. Okay. Work out these problems. Feel free to contact me for any doubts. Pavan Kumar Reddy _ @VNRVJIT.in. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.